So how does this link into anomalous event detection? You're probably wondering, like, did I sign up for an LLP course? No, okay, we're not doing natural language processing, but there's a lot of lessons that we can learn from other areas within machine learning, especially as this, this field is really just developing. A lot of these tasks that people are using are often transferable. And we saw this last week, even when we were looking at object detection methods, using them for improving classification with imbalanced data sets. So the pseudo-algorithm that we're going to use for this is pretty simple. For a given event, you're going to randomly select a feature. So that event, like we said before, that could be a person logging on with a particular IP address on a particular day, particular time, using a particular device, accessing a particular server. Now, for that feature, you're going to randomly select a new category. So you might replace Monday with Saturday, which would be sort of unusual if it was a real 9-to-5 business. People work Monday to Friday. Nobody should be working on a Saturday. And you repeat this k times on all samples. So you want to have a high enough number that you're creating enough of enough negative samples that it learns the true distribution, but obviously not too many that you're going to run out of hard drive space. And then the task for the algorithm is to classify the real versus the fake data. So this is pretty simple. There are a lot more subtleties, so we're going to get into those and a little bit more on how we're going to do the sampling. Finally, then you're going to test on the real data, and you're going to determine, like, well, are there any anomalies in this data, or in the future, you can use this so that you can see if any anomalies do crop up. So what are the considerations that you need to take into account when you're doing negative sampling? So, well, the negative sampling rate, which we've discussed a couple of times, which is k times the true samples, that's very, very important, and we'll see why. What features you're actually going to vary and what features you're going to keep fixed. We'll get into that in a little bit. Sampling procedure. So maybe for this given feature that you're now going to change, well, what category do you change it to? What value do you change it to? So what day of the week do you change it to? Do you just uniformly select between all possible 7 days of the week? Do you pick the most probable, so it's more likely to be a Monday to Friday, or do you pick the least probable, which is more likely to be a Saturday to Sunday? That will be a decision that you need to make when designing this algorithm. And then the last kind of consideration I'm going to discuss today is hard negative mining, which is really just all about ensuring that you've got a really challenging negative sample for the classifier, but hopefully not too challenging. Okay, so let's discuss the negative sampling rate. So this figure we have here is from a paper called Cadence, which is conditional anomaly detection for events using noise contrastive estimation. Which is, good acronym. Yeah, I'm impressed with that one. What they're plotting here is the precision recall curve for their anomaly detection using a particular data set that we will be using in the workshop. And they're plotting this precision recall curves at different ratios of negative samples to true samples. So they're going from a negative sample rate of 1 all the way up to 15. And the area under the precision recall curve, as you can see, increases significantly until about 10 to 15. The idea here is then that you need enough counterexamples to learn the true distribution, okay? However, you're going to be limited by, as k goes to infinity, you're going to have an infinite, impossibly large data set to process. And also, the data set's going to become significantly imbalanced, so it's going to become a lot more difficult to perform classification. So you need to figure out what is a good k to use. Here, I think they settled on 10, which kind of makes sense. In the literature, a lot of the times with word embeddings, you see k roughly equal about 20. So in this kind of range where you've got a significantly larger number of negative samples, but still something that's tractable, something that you can actually work with. Okay, so feature selection. Well, some of these features, when you decide to do this, some of the features you might want to use, some of them you might not want to use, some of them you'd like to keep fixed and not modify, some of them you definitely will want to modify. So in red, I've marked the ones that you would want to keep. So this is an example maybe of, you've got process logs of all the different devices that your employees have in some enterprise setting. And so we know that some employee used their iPad to do a FaceTime call, and this employee is a project manager. Right. And so it wouldn't make any sense to change the OS in this example to something like Windows, because you're never going to well, never say never, but it's very unlikely that you're ever going to have a Windows operating system on an iPad using FaceTime as a process. Maybe there's some homebrew dude out there who can tell me otherwise, but the reality is this is going to be a very unlikely thing that's going to happen. Likewise, we probably don't need to know the employee number. You might want to learn specific things about specific people's behavior, but it's generally not a good idea because it's not going to be a very generalizable model then. What you would want to know is it typical for, say, a project manager with this role to be doing this? So you'd like your model to be as generalizable as possible. So maybe you should remove things like the employee number because this isn't really something that is relevant to your model, and it's just going to create more overhead. Okay, so then sampling procedure. So it's all about striking a balance. As we've already seen, pure noise is going to be way too easy for the classifier. But on the other hand, you can also make it impossible for the classifier by sampling from the true distribution. So you could literally just grab another row from your data and then just say, is this row real or is this row real? And they're both real. And so it's going to be impossible for that classifier to tell. So you have to be careful when creating these negative samples that you're not creating something that's actually realistic. So what is the right fit? Well, like we had already said, selecting one feature, that's generally good. Out of all the features that you have, you just focus on one feature for that given row at that given time. So you randomly select one feature, and then you decide what value you're going to change for it. And then you repeat this so many times for each row. Okay, well, then within that feature, how do I sample a new value? So could you use a uniform distribution, the most probable, the least probable? Again, this is something that you have to decide yourself. It would be my guess that it's not something that I've actually investigated, but it would be my guess that the most probable events are going to be closest to your true distribution. The least probable are going to be the furthest, and the uniform distribution is going to interpolate in between. So depending what your needs are, pick the distribution that you think works best. Okay, so here's an example of maybe creating a negative sample for event detection. So this event here, we've got Bob, and Bob is using his iPad, and it's a Monday at 2 p.m., and he's logging into his email from Toronto with this IP address. Okay, so that is a normal event. Bob likes to use his iPad to check his mail. He works Monday to Friday. It's 2 p.m., so he's just after coming back from lunch or whatever. So this is all very, very normal for our data. Now, you could change everything if you wanted. So it could be Jerry, who was the co-op who no longer works with us, dialing in from Moscow on a Saturday using Pam's iPhone at 2 a.m., and he's accessing client database 1. So that's really, really bad, all of those things. But it's also just way too obvious that this is a bad example. And you're not going to create a very challenging example for your classifier here. So if you change all of these values, then it's going to be way too easy for the classifier, and you're not really going to learn anything to do with the true distribution. So you're better off just changing one value. So maybe Bob then is accessing the client database, and Bob should not be doing that because Bob has no business accessing the client database. Bob works in HR. He shouldn't know anything about the clients at all. Okay. So the last consideration that you might want to make, although really it's kind of just an extra when you're doing this, is hard negative mining. So what is hard negative mining? Well, hard negative mining is all about coming up with the most challenging examples, but hopefully not too challenging. So there's two different methods. Let's talk about method A. So you alternate training and sampling on a small subset of data. The negative samples that are correctly classified are marked as easy, and we remove those. The hard examples are the ones that were incorrectly classified. So we hold on to those in the training data, we generate new samples, and then we repeat the training. And maybe then the hard examples it has learned, so these hard examples are no longer hard. So we mark them as easy, we remove those, we generate more data. So hopefully you should converge at some point that you really tapped out all of the possible hard samples that you can use. That's why it's called negative mining. The other approach you can take is that, again, you randomly select some negative samples, you train a model to convergence on a small subset of the data set, and you test it on a larger data set, and you harvest the false positives. Okay, so it's kind of similar, and then you retrain the model on the false positive examples. I would probably recommend method A here. I think it's you get more guarantees and convergence, and you can retrain more times without feeling like you're going to overfit. But I'll leave it up to you guys if you ever want to use this, which method to approach. Okay. All right, so what are the limitations of hard negative mining? Well, we're assuming that your training data is mostly going to be made up of normal events. If you have a large number of abnormal events occurring in this data, well, then you probably should maybe use another method. What that number is, hard to say. Certainly if it's above, I would say 10%, you're really pushing it. I would probably hope that it would be at least below 1% of all possible events would be abnormal. So you want to assume that your training data is going to be normal, because that is what you're going to end up skewing and modifying and making abnormal, right? False positives are obviously still going to be a problem. We're not actually determining malicious intent here. So if Bob pulls an all-nighter on a Saturday while visiting his parents for the holidays, all of those things are going to, trip an alarm, because he doesn't normally work on the weekends. He doesn't normally work at 2 a.m. He doesn't work from this IP address usually, and he's supposed to be on vacation right now. So all of these things should be, really, really tripping alarms. But maybe Bob is going for that promotion, and he really, really needs to get this project done. All right. So another issue, limitation, is temporal coherence. So this algorithm doesn't take into account time or dynamics. So, several anomalous events in sequence do not get priority over these same events occurring randomly across time. However, they obviously should, because, say, for example, somebody had broken into your network. Maybe it's a red team event. Maybe it's actually worse. It's a threat actor. So that they're now doing lateral movement and privilege escalation, and they're moving their way through your network, getting towards your crown jewels. You should be seeing these events flagging again and again and again. So if you train an algorithm to detect anomalous events, fine, it'll catch these, but it won't add any more importance, saying that, hey, the last 3 triggers we just had were all within the last hour. So that's something we should really be worried about. So this is something that is an additional ask, or you would have to come up with a new model that would take that into account. Okay, and finally, I just want to caution that we're applying this to categorical variables. So if you wanted to create negative samples for continuous values, of course you can, but you need to take care and make sure that you are treating them with the respect that they deserve according to their distribution. So, is this a normally distributed data set? Or is it uniform, or is it bimodal? Whatever it is, or maybe you should perform some function so that it gets towards a uniform or normal data distribution, so that it's a lot easier for you to sample from. So it's absolutely a possible technique that you can use in continuous variables, but it's just something you have to bear in mind, that you need to be aware of what that distribution might be. Okay. So classifying with this, any decent classification method should work, so long as you have a decently large number of parameters that can learn this data distribution, because this is not something that you can learn with just a simple logistic regression, right? But maybe you can use it with neural network. Maybe you can use it with XGBoost. So the advantage of using a neural network is then you have a learned embedding at the end. So you can use this learned embedding for downstream tasks. So the previous slide where we're talking about dynamics, this would be an example. So maybe you have learned these are anomalous events, these are normal events. You now have an embedded vector for all of the events that you can possibly have. You then take those events and then you look at the sequence of events. And so you start training with sequences of events. And maybe your labels are saying, well, there's some anomalous events in here, and you have to guess how many anomalous events are in the sequence or something like that. So if you trained a recurrent neural network with this, then you could use these embedded vectors as your data. You could train your recurrent neural network, and then you would now have a dynamic anomaly detection algorithm. The reality is, though, that like, GPUs are expensive. Deep learning, it's not always an option. There's a bit of a learning curve, and you don't always have these resources available to you, or you might be even limited on your tech stack for security reasons, or whatever else. You might not be permitted to install PyTorch or TensorFlow or Keras. So GPUs are just not an option for you. But I would definitely say that XGBoost should be up to the task, because at the end of the day, what you're trying to do is classify, is this normal or is it abnormal? And that's it. Getting an embedding out of it is just an added bonus. Definitely a really good one if it's something that you want to use for downstream tasks later. But at the end of the day, you should be able to perform the task that you need using something like XGBoost, which is an amazing classifier. Probably the one that I would use for most binary classification problems. Okay, so at the workshop, we're going to be using this Los Alamos dataset. The Los Alamos dataset has 58 days of data, 12 gigs of compressed data, which comprises of 1.6 billion events in total from over 12,000 users, over 17,000 computers, and nearly 63,000 processes. So this data includes auth events, process events, network flows, DNS lookups, and red teaming, which is amazing. Like, this is just the holy grail of cybersecurity data. This is huge. So we're going to be processing all of this on Thursday. No, I'm just kidding. We will just use a sample. There's no way in hell that we can actually process this data anytime in the next month, given Google's collapse resources. So we're only going to be looking at a small subsection, I think a few hundred, users. And just as a note, so some of the capstone projects are using this data set. Likewise, there's no expectation on anybody to use all of this data. This is something that you would need a lot of patience for, or a large distributed system for, or something that you can really process this quickly and efficiently. So sampling this data is totally fine for the capstone project. I would really recommend considering how you're going to sample this. Do you randomly sample rows? Do you randomly select users? Do you randomly select computers? Do you just sample a few days? That's really going to be up to you, but bear in mind certain things like the structure of the network. Bear in mind that when red team events might be occurring, if you're trying to do some kind of anomaly detection, the red team events, I think, occur day 9 or something. So if you are only looking at the first 2 days of data, you're not going to find really anything weird or anomalous there. So bear in mind all of these things and how you would like to sample this data. And also bear in mind that it's going to take a while. So how you do the sampling is very important, because some methods are more efficient than others. Okay, so let's conclude what we've been talking about today. We can do anomaly detection with high cardinality categorical data using noise contrastive estimation. We can learn this probability distribution that generates events. So we can say, given this, given this feature or these sets of features, what is the probability that this is normal? And we can say that low probability events, these can be classified as anomalies, right? And I think we learned that doing this requires some careful consideration for sampling. So things like your negative sampling rate, how often, how you're going to retrain this, hard negative mining, exactly what you're going to be sampling. Is it one feature? Is it 2 features? Which ones are you keeping fixed? Which ones are you getting rid of? Which ones are you letting vary? Maybe you could do something even jazzier by like saying, okay, so I know that my operating system is iOS 13, but maybe the application doesn't have to be FaceTime. Maybe I can change it to something else. Maybe I can go through the App Store and pick all of the possible applications and get some really weird ones and throw them in there. You can build it whatever way you want. Just make sure that what you're trying to do is a reasonably logical negative sample. It should still conform within the bounds of reality. It's just, the idea is then that it should be very unusual, having said that. So just to reiterate, you should not have Windows running on an iPad that is currently running FaceTime, all right? Likewise, Android or Linux or whatever else. So consider what is actually going to be realistic, excuse me, and also what is going to be very, very anomalous, but possible. Okay, so next week, so that was it from me for the past 2 weeks. Thanks for listening. You get a break from hearing about my voice croaking next week because Sahara will be taking over and she'll be talking about graph theory. So we're going to be catching anomalous behavior using graph theory techniques. So thank you for listening for the past 2 weeks. I really hope that you've enjoyed them. I look forward to interacting with you guys next Thursday in looking at this anomaly detection technique that we're doing. And if you have any questions, well, please think of these questions. I really, really enjoy chatting with you and workshopping these ideas and getting ideas from you guys. So any questions, ideas you have on Thursday, please do share them with me or with Willie. And hopefully we can have a really great workshop in week 2 with a lot less code to work with. Just we're going to streamline it significantly, so you won't have to worry too much about filling in code or anything. It's more just going to be operating that code and then seeing how it performed. All right. Okay, so that's it from me, and I'll see you guys, some of you guys, on Thursday. And for the rest, well, thanks for watching, and probably see you in the cybersecurity or machine learning circuit at some point. All right, have a good one. See you. Bye.